Hi everyone. In this video, I'm going to walk you through a simulated version of a project we completed for a client. The original project involved geocoding address data and analyzing spatial trends to support planning and decision making. Due to the sensitive nature of the original data and in line with data protection and privacy requirements, none of the location data shown in this demonstration is real. The statistical values used for analysis and data edging were sourced from StatsSA as well as other reputable sources. To start, we took the provided address dataset and performed geocoding to convert those records into spatial point data. Here you can see the geocoded locations, that's all these brown points on the map, along with a central reference point used for analysis, that's this little pink dot here. All of the spatial data shown here is dummy data. It was being generated to reflect realistic patterns using place-based data, which are the centroids of suburbs, towns, and cities, all of which is derived from OpenStreetMap data. It does not represent any real individuals or actual client information, ensuring full data privacy and security. Once the data was spatially enabled, we carried out a series of spatial analyses to understand the behavioral patterns and geographic relationships. To start with, we did some travel-based analyses. The travel distance and travel time were calculated. So I'm just going to show you the travel distance first. These analyses were calculated using the provided data to identify how far and for how long individuals were typically willing to commute to the location. This helped refine a realistic catchment threshold. So you can see here these areas are all areas of equal distance from our starting point, and they are using the road network as their distance. So we go all the way up to 25 kilometers because that's how long people are willing to commute. We then also do the travel time, and this looks slightly different. These are using isochrones or lines connecting areas of equal time, and these do rely on assuming that you are traveling at ideal speeds along the road network. Again, like there's some anecdotal evidence that shows, for instance, driving from over here in this 30-minute zone to our end location will not take 30 minutes, and traffic will take over an hour. We then looked at some spatial distribution. A density analysis was used to pick up areas where populations are most concentrated, giving a clear visual indication of where the highest number of individuals are located relative to our end location. And so you can look at it, this data is quite sparse and quite spread out. It's not the same as our actual data that we used, but you still have these little hotspots. You can see here there's quite a nice glowing yellow area, a couple of little yellow areas that are showing hotspots. Building on this, we then decided we were going to perform a clustering analysis. We chose to do a DB scan because it is well suited for identifying clusters of irregular shape and can effectively handle outliers without requiring a predefined number of clusters. This clustering analysis was done to identify natural pull areas, and you can see that in the DB scan we used a radius of 1,000 meters around each point to identify what consists of their cluster. And you can see we've got some clustering there, some clustering there, some clustering there. We do have some very dispersed points. In our actual data, our clusters were much more significant. To incorporate some demographic data, we carried out a socio-economic analysis using mesozones. Mesozones are a national spatial grid of approximately 25,000 units per zone across South Africa. This analysis allowed us to assess whether certain income groups or demographics were more likely to be associated with our end location, which is useful for future planning and resource allocation. So you can see each of these different polygons here. So we have the darker blues, lighter blues. Some of them are together because they have similar values, but all these polygons are mesozones. And then these points are our addresses, and they use the demographic data pulled from the mesozones to just style them to show the predominant demographic in that mesozone. We then used all of these insights to identify potential growth areas. The analysis combined factors such as the number of families, income levels, population density, and the number of individuals within a target age group to highlight areas where future growth is most likely. We started off just doing a basic yes or no potential growth. So we have the green areas are areas of potential growth and the red are areas of non-potential growth. This data does cover the entirety of South Africa. I will be focusing though on Johannesburg and just north of Johannesburg for the moment because that's where our analysis was mostly done. So we had our 2-class potential growth. One of my colleagues then had the idea for a 4-class potential growth, and that was quite cool because we then went from areas of yes or no to areas of high potential growth, areas of normal potential growth, areas of low potential growth, and areas of non-potential growth. We also had one final potential growth area, And that we use incorporating our isochrones from earlier, our areas of equal time. We then have these areas of potential growth that have this nice gradient saying the closest areas that have potential growth within 5 minutes, 10 minutes, and so on. So then our final analysis we did was we explored accessibility through route and public transport analysis. By incorporating cloud train infrastructure, we were able to identify potential routes that could extend accessibility to the location, allowing individuals from further areas, particularly the north of Johannesburg, to access it without requiring direct commuting. So that means you don't have to get in your car and drive. And so what we did there was we'll start off with the duration. I'm just going to zoom to groups so it gives us a nice look. So you can see we have some isochrones here. And so what we did here is the duration. So these blue dots are the Gautrain bus stops. The gold line with the black outline is the Gautrain's current bus routes. And then the black line with the cross-hatching is the actual Gautrain line. These blue and purple lines are our calculated routes using time. So you can see like the longest blue routes here are going all the way up to 43.8 minutes. Not ideal for traveling on a bus or doing a central commute, but we restricted them down for our end client. We then also did a distance-based analysis. And this goes from all the Gautrain points all the way down. And you can see we set a maximum of 45 minutes, which is why some of these points up here weren't included in the time. But you can see our longest travel distance is 61 k's, and that's still not ideal. But for our end client, we can then we shrunk these down so they could focus more on this more concentrated area of where they would run their buses to help utilize the Gautrain infrastructure. Across all of these analyses, we developed structured QGIS models to ensure that the workflows were fully repeatable and scalable. This means that each process, from the travel calculations through to the density, clustering, and socio-economic analysis, were built as model-based workflows rather than one-off manual processes. By doing this, we were able to standardize the analysis pipeline, allowing the same methodology to be applied consistently across the different datasets and updated inputs to be generated with minimal reconfiguration. This is particularly important because most of our data came from 2011, from the stats 2011. Sourcing the later data was an issue. For future growth, we applied a modeling approach using long-term averages derived from historical data. These averages were calculated using multiple reputable sources, including Stats SA, the Bureau of Market Research, World Bank datasets, and various South African government departments. I'm just going to show you the model there. So this is the model designer in QGIS. We use this to build everything. So I will show you our projected household size data for the moment. If we scroll down, you can see here we have this formula that was done. Instead of relying on short-term fluctuations, we use smooth trends to estimate expected growth over time. So that's where these values come from. This provided a more stable and realistic projection of growth. These calculations were then applied spatially, allowing us to estimate how the distribution of the data might evolve. So this is just for aging out the household data. We have the different models for aging out other things. Just to, while we're in the model builder, I can show you our most complex model. This is how we built out and we could age out our data for our potential growth areas. And it takes in all those different calculations that we did for our age data and then allows us to make an informed decision into our end data. So the data I've been showing you now has been our 2026 data. So you can then see that we can predict out from 2011 to 2026, or any year particularly after 2011. This visualization highlights areas of expected growth and changing patterns, giving the client a forward-looking perspective to support planning decisions. But we can age out the data and allow the client to make informed decisions going forward. In conclusion, this project demonstrated how raw address data can be transformed into actionable spatial insights. From geocoding through analysis, automation, and forecasting, the final outputs illustrate how the client was provided with a clear understanding of both current trends and potential future growth. The original project was completed and handed over successfully, meeting the client's requirements and supporting their strategic planning objectives.